Hello, my name is Nicholas Boyce, and today I'll be giving a presentation on reclassifying human development land cover classes to improve non-forested estimates. Starting with a little bit of background, here at the Haman Lab we're working on this diverse project assisted migration tool, which is a tool meant to inform foresters on where they can supply their provenances from, so that trees planted at a particular target site are well adapted for future climates. However, we have identified a few issues with our tool. One of these is some misleading non-forested estimates. So here we see the predictions for the Sundry Forestry Management Unit as an example. And here we're predicting a 30% increase in non-forested area by the 2080s from our baseline, which under most circumstances would be pretty alarming if you're a forester. In order to understand why these predictions might be a little misleading, we must first look at how we are getting these predictions. So the methods that underlie these tables is that we take our target site and we take the projected climate for that target site, so in this case 2080, and we find current ecozones that are the shortest climatic distance to our target site's projected climate. So we call these our climate matched ecozones, and we get a weighted average among all these climate matched ecozones. So if we zoom in on one of these ecozones, we might see something like this in terms of land cover, some forest, some grassland, some cropland, and some urban. Now the issue is, and why this is perhaps misleading when applied to our projections, is that the lower amount of forest coverage in this area is not only due to climate, but also in part due to human development. So we have some area that would have been forest if it was not converted into cropland. In order to improve non-forested estimates in our diverse SST predictions, we are going to create and validate a model for predicting land cover class based on annual climate, and then create and validate a model for predicting expected land cover class in the absence of human development. So in essence, we want to reclassify cropland and urban as what it would have been if it was never developed. So in terms of methods, for our data, we used a 5-kilometer points grid across North America, which was further systematically sampled to just under 280,000 locations. We also have climate NA generated annual climate variables for the 1951 to 1980 normal period, which is our 1960s baseline. And we also have land cover raster from MODIS from 2005. Our random forest classification used two models. The first one just predicts land cover class as a function of annual climate variables. And the second one does the exact same thing, except we have removed the human development classes, cropland and urban, from the training data. Moving on to results. Here's the confusion matrix from model 1. So this will give us an idea of how accurate the model is and what classes are being confused as others. There's a lot of information to unpack here, so I'll just refer to a couple things. Our most accurate class was urban and built up with an accuracy of 88%. And our least accurate class is temperate and subpolar grassland with just over 25% accuracy. Now for model 2, we of course see that urban and built up and cropland are predicted 0% of the time and are instead re-predicted as other classes. So here we see that temperate or subpolar broadleaf deciduous is the most popular prediction with 48% for urban and built up and 35% for cropland. We can also map out the land cover classifications in order to get a more spatial perspective. So here we see the original MODIS land cover classifications for North America. Here is Model 1, the random forest predicted land cover classes by annual climate variables. And here's Model 2, the same, but with urban and cropland removed. So we can see that that large swath of cropland in the middle of North America is now gone and replaced with natural land cover classes. So in terms of conclusions, for our first objective to create and validate a model for predicting land cover class based on annual climate, I'd give it a yellow light. We did successfully create a model, but the accuracy leaves some things to be desired. And this is the same for our second objective, creating and validate a model for predicting expected land cover class in the absence of human development, where the accuracy of our predictions leaves some room for improvement. In terms of future directions, our priority will be model refinement. So in order to improve our accuracy of our models, we may want to remove irrelevant classes, add some other predictors such as vegetative cover, or use some more powerful models such as digital neural networks. We're also looking into doing some k-means clustering with the integration of climate data with tree species range maps to create bioclimatic zones, and then integrate all of this with the diverse SST to improve non-forested and species frequency estimates. Thank you for listening.